Good morning, folks. I have decided that it's time for me to get started. Welcome to Introduction to Containers for Scientific Container Native Workflows using the Charliecloud container runtime on the ACES cluster. My name is Richard Lawrence. I will be your instructor today. This course is designed for a student who may never have used containers before, so I begin by explaining what containers are and what Charliecloud can do for us before we get started with our first containers. For scientific containers, the main topics are where do we get our container images and how do we use them to execute scientific software. So we won't be discussing building images because that is a topic from the fundamentals course, which I did a couple weeks ago. So we have learning resources. We have a knowledge base. We have a YouTube channel. But the most important learning resource is this slideshow. So this slideshow can be found on the course webpage where you registered. Recall this webpage that you probably saw when you registered. If we scroll to the bottom, you can see that the slides for today are available, and I'll go ahead and drop the link directly in Zoom in case you don't feel like navigating our webpage. So I've just dropped the link to this slideshow in Zoom, and I'd like you to open it so that you can follow along, because there will be some points where you might want to copy and paste some code from the PDF into your terminal to reduce the chances of an error. So having the PDF open in another tab is very helpful. Let's talk about containers. So a container is a process that has its own view of local resources. So examples of local resources include the file system, user IDs, the network. There are other resources. For today, we're focusing on the file system as the main resource that the container views. Good morning, Carl. Thank you for joining us. You just missed, I distributed the link to this slideshow. So you probably want to open up this slideshow to follow along with us. So a normal process sees the physical file system, which I represented here using the disk image, the graphic of an optical disk, and therefore but a file system can contain within itself a small sector which represents a smaller file system, and we call that an image. A container sees the image as though that were the real physical file system instead of the real physical file system. So when you do it this way, you have complete control over what files are available in the container. Why do we use containers? Well, this is Containers for Science, so we like to be able to collaborate with our colleagues, and containers are shareable because you can upload your images to repositories and use images that were shared by others. Containers are portable because you can use images on any computer with the same architecture. I think this is a typo. I think it's meant to be 8664. I can never remember. Good morning, Tanaza. Thank you for joining us. You've just missed, I distributed the link to this slideshow. So I'm pasting that in the Zoom chat so you can follow along. And finally, containers help with reproducibility, because if you are using software that's in a container image, then you're largely unaffected by changes that happen to the real physical file system. For example, if the system administrators decide to upgrade the operating system, if your software lives on the file system with the operating system, then it probably is broken. But if your software lives in a container image, then it's probably fine. So you can redo your work at a later time, confident that you'll get the same result. So what do we put in container images? You may have heard of a similar concept called a virtual machine. In a virtual machine, you have a guest operating system kernel that is running in memory. And in order for an operating system kernel to run, it has to be in charge of some hardware because that's what operating systems do. So you have a virtual machine manager that is emulating some hardware for the guest operating system to be in charge of. But operating systems and emulated hardware are pretty large in memory. So there's a limit to how many virtual machines you can have running on a node. After a few, your memory's full and you won't be able to do anything useful. So the strategy of containers is we're not going to have a guest operating system kernel. We're going to use the host operating system kernel. So the only things that go in the container are the files that make one flavor of that operating system different from another. So, for example, guest libraries here represents the part of Red Hat that makes Red Hat different than Ubuntu. But since all the variants of Linux share the same operating system kernel, that part we don't duplicate. And the container runtime translates between the guest libraries and the host operating system kernel. So some popular container runtimes. Containers have actually been around for a while, but aside from some extreme Linux nerds, nobody knew about them. It wasn't until Docker came out that containers became really popular in science because it allows researchers to share software on their personal laptops with their colleagues. And that works really well. So there are lots of Docker images in the wild in use today. But Docker was designed for your personal desktop. It was not designed for a shared high-performance computing cluster. So we have other container runtimes that were developed later to address that need. Singularity, one of the first, which we have on ACES. Shifter, which is mainly for Cray systems. Charliecloud, the one we're going to be talking about today, and Podman, another popular choice that we don't currently have on ACES. So let's talk about Charliecloud. Charliecloud is a lightweight, fully unprivileged container solution, which is presented by Los Alamos National Laboratory. Recently, Charliecloud joined the Linux Software Foundation as a founding member of the sub-foundation named the High Performance Software Foundation. So soon we're going to start seeing technical advisory committee meetings, which I hope to attend. It's very exciting. So what features does Charliecloud have? Charliecloud is a container runtime and an image builder. That's important because if you are going to be modifying images, you want to be able to do that in the same place where you're going to be running your images. Otherwise, it's a hassle moving your images back and forth between different systems. Charliecloud can read and convert Docker images. That's important because Docker has been around. Docker is the most popular. The majority of images that are out in the wild are Docker images. So being able to use them gives you access to the vast majority of all the container images. The file system inside the container is isolated. That's important because you want to be able to ensure reproducibility of your work. And the user inside the container is isolated. So that means inside the container, you can rename yourself root if you wish. If your software says, I only work if my user is named a certain way, then you can rename yourself inside the container to whatever you like. But the rest of the cluster still sees you as your regular self. So privileges are not getting involved in this. And Charliecloud works with high performance cluster technologies mainly because their strategy is to get out of the way and let the user do what they need to do. So you can read more about the Charliecloud manual, which is currently on GitHub, but will be moved to GitLab soon. Charliecloud is available on ACES. So we have a module system that allows you to load software modules that have been installed. So the command is just module load Charliecloud. You can pick a specific version, but for today's tutorial, it will not matter. Charliecloud images can be large on disk, so you need to be aware of your storage quota. For example, I forgot to put it here, but for example, your Scratch directory has a much larger quota than your home directory, so we'll prefer that. And then the next one is some container activities, maybe too CPU intense for the login node. So if you're going to be doing a very large image operation, then be courteous to others and use a compute node. And finally, some container activities may be too I/O intense for the shared network file system, which is a Lustre file system. And so when we're doing large image operations, we will be doing that on a local file system, which is NVMe and not Lustre, so that we don't put a huge load on the shared network file system that we all depend on. And I'll teach you how to do those things when it becomes relevant. So who's ready to get started? Anybody in Zoom want to throw up a reaction to let me know that you're excited to get started on your first container runtimes? Yes, Sajesh, I'm happy to see you're excited to do it. Thank you, Carl, for reacting. Thank you, Tanaza, for reacting. Thank you, Daniel, for reacting. So in order to get started, we need to log in to the ACES cluster. Thank you, Shuofei, for reacting. That's everyone, so we're all ready to go. We need to navigate to the ACES portal, which is the main way that you're meant to be accessing the ACES cluster. So there's more than one way to get to the ACES portal. I can just drop this URL into the Zoom chat for your convenience. But in general, the way you do it is by using our home page. So if you're on our HPRC homepage, we have a portal menu, and one of the options is the ACES portal. And it says parentheses access because we will be using your access credentials to authenticate to the ACES portal. And since I have recently authenticated, I actually get to skip that step and it just takes me directly to the ACES landing page. Let me make my font a bit bigger. So the landing page has the message of the day, which says the maintenance was successful. Yay for maintenance. So I'm returning to my slides. When I didn't have to authenticate because I recently did that, and your browser remembers, it keeps a token from the last time you authenticated. So if it was recent, it will just reuse that token. But if you haven't authenticated recently, then it will redirect you to the Access login page. So you have to use the Access login page to select your identity provider, whichever one you selected when you signed up for Access. So for me, that would be Texas A&M University is my identity provider. If you're using the Access CI as the identity provider, then you just get a normal looking Access CI login. And whenever whichever way you log in, after it's successful, it will automatically redirect you back to the portal where the link was trying to take you. So would anybody be willing to throw a reaction in Zoom if you have successfully authenticated with Access and reached the ACES portal landing page? Yes, okay, it looks like we're ready to proceed. So my next slide is that you need a shell terminal in order to do some command line activities. So we have a menu named clusters, and under the clusters menu, there's the ACES shell access link. So the clusters menu, ACES shell access, then it pops open a new tab. Let me make my font a little bigger. And you get the message of the day, and then you get your disk quota. So you should watch your disk quota, make sure you don't accidentally overfill your home directory, because that will immediately cause problems for you. So my home directory is fine. So I'm just going to clear my screen so we have a nice tidy screen to look at. So I landed on ACES login 2. The most common login nodes I see people landing on are logins 2 and 3. Would anyone like to respond in the Zoom chat which login node you landed on? Good morning, you chat. Thank you for joining us. I would like to drop the link to today's slides in the Zoom chat for you so you can follow along with us. So far, we just talked about containers, and now we're logging into the ACES portal. So Tanaza and Carl both landed on ACES login 3. I landed on ACES login 2. Those are the most common nodes I see people landing on. They're both perfectly good for this, for today's exercise. So what do we need to do on our login node? We need to set up a workspace for doing the activities. And as I previously mentioned, we don't want to be working in the home directory because we will overflow your home quota if you do that. So we're going to go to the Scratch directory. So that's CD $Scratch and make a space for yourself. So you could name it CH tutorial or whatever you want. It's just somewhere to keep your files. Let me quickly do that. CD Scratch. Where is Scratch? There it is. Make myself a CH tutorial. Actually, I already have one, so it's going to say I can't do that. So I guess I'll just go into the same directory and see. I have previously done this, so I already have most of these files. You won't have a copy of these files yet, but you can get a copy for yourself if you want, because we have the training directory, Scratch Training Charliecloud, which you should probably save in a variable in case you need it later. Export training equals Scratch Training Charliecloud. And we'll ls the training directory. You see that there are already files there that are available for you to use. If you need a copy of one of these same files, they're in the training directory. So you don't have to worry about not having the file you need. You can go grab a copy for yourself if you need it from the training directory. And then the last step is we need to execute module load Charliecloud to make sure Charliecloud software is available in the path, the execution path. So right now, if you tried to execute Charliecloud, it would say, I don't know what that is. Then you do module load Charliecloud. And now Charliecloud commands are in the path. So I loaded Charliecloud 0.33. Apparently, I think that's the default version on ACES right now. Probably the latest version on ACES right now. I think that's how we have it configured. I think default is just latest. So please do give a reaction in Zoom or speak up in chat when you have finished these steps so that I will know that everyone is ready to proceed. Okay, 3 reactions in Zoom so far. Very good. I think that's a 4th. What is module list doing? Module list is just to confirm what version of Charliecloud has been loaded. So we didn't specify a version in our load command. So we would like to check what version actually got loaded, and module list is telling us what it did. it's just a good habit to double check what you've done. And if you're new to these things, you don't need to execute module list if you're confident that module load worked the way you want because you've done it before, for example. Okay, so let's move on and get started with our first container activities. So the first container activity is going to be to fetch an image from a repository. And we're going to use the chimage tool to do that. And the command for fetching images from repositories is chimage pull. So generally you would chimage pull from a URL. So a website where there's a repository followed by the name of the image. But the default repository is Docker Hub because it's the most popular. So if you don't specify a URL, that's where Charliecloud will go looking for your image. So I have picked an image here that is available on Docker Hub. Its name is Alma Linux. Alma Linux is a small Linux distribution that is published by Docker community for Docker users and also other container runtime users. So let's fetch a copy of Alma Linux from the repository. And similarly, chimage list is going to confirm what we have done. So after you pull, it's going to save it on disk, and then chimage list will tell you what it actually pulled. So chimage pull Alma Linux :8. And then it says done, and then chimage list to confirm what we have done, and it says that there is an Alma Linux 8 on disk. Where is it on disk? That's a question we can answer. So it is on disk in a file path that is being stored in a variable named chimage storage. So if we use that variable chimage storage, we can investigate where Charliecloud has put that file on disk. Echo chimage storage. It is located in a directory in temp. So temp is the local file system for this node. It's an NVMe. So that means that already we're following my recommendation of keeping our images on the local file system while we're working with them. So that's good. We're off to a great start. And let's investigate what is located in this directory. So ls chimage storage /img, and we can see there's an Alma Linux 8 directory. So that must be where Charliecloud put Alma Linux 8. And now we will investigate what is inside the Alma Linux 8 image. So we will compare the contents of a file that is present both on the real physical file system and in the image. And the name of that file is Red Hat release. So the ACES login node has a Red Hat release file because we are running a Red Hat Linux. So let's hit the etc. Red Hat release file with cat, and we can see that this ACES login node is running Red Hat Enterprise Linux release 8.8 UTPA. Now we need to investigate what is in the file system of the image. So the way we do that is we launch a container process that sees the image and then do the same operation, cat the etc. Red Hat release file. But that time, the second time, it will not be seeing the etc. Red Hat release file that's on the real physical file system. It will see that file that is present in the image. Somebody's calling me. That's weird. Well, too bad. I can't take a phone call right now. So in order to launch a container process, we use chrun. So the syntax is chrun, the name of the image that your process will see, followed by the name of the command. And we just need a bash terminal in order to execute cat red hat release file. So it's chrun alma linux 8 bash. And now my terminal has changed. My terminal is bash $4.4. It used to be user at login node, then it changed. And the reason is because inside the image, this bash executable has no knowledge of what my terminal is supposed to look like, so I got a default looking one. And what were we going to do? We were going to cat the etc red hat release file. Oops, not that one, that one. And inside the image, we have Alma Linux release 8.10 Cerulean Leopard. So same path, different file. And that is the first time I discovered this. It actually completely blew my mind. This changes everything. Whenever you're done with that bash process, by the way, you click exit to stop that process. And now we're back in our regular bash terminal that sees the real physical file system. Is anybody willing to throw the thumbs up in Zoom if you have completed this exercise and you compared the Red Hat release file inside and outside the container? Then congratulations! Welcome to containers, the exciting world of containers. I am very pleased that you have chosen to come and learn containers with me today. And I think that if you tell your friends that you know what containers do, they will certainly be impressed. And now it is time for a short break before we move on to our next activities, because my mouth is getting dry and I need a sip of water. So we're going to be on break for about, I guess, 5 minutes. We haven't been working very long, so we don't need a very large break. So we will return at 10:38 in Central Time. So break until the 38th minute after the hour. I'm on Central Time so that's 10:38 for me. Howdy students, welcome back from your break. Now it is time to learn about container image sources. Where do we get container images from? I previously said that we were going to fetch Alma Linux from Docker Hub. That is the most common repository for images. There are others, including Singularity. NVIDIA has a GPU Cloud, Quay.io, and Biocontainers. We do have examples for these on our Singularity page at the moment. But the syntax is similar. So let's take a closer look at a Docker Hub example repository. So Docker Hub is kind of like GitHub in that repositories are named in the form of a group/repository name. So in this one, the group is named Jupyter. So these are the Jupyter developers, and they created a container image named SciPy Notebook, which I guess is telling us that they installed scientific Python into a container image. And also probably Jupyter Notebook is in there due to the name of the group itself. So within each repository, there will be a series of images that are tagged. The tag describes how and when it was built. So you could have a tag that says it's made, what kind of what kind of flavor of Linux is in there, what version of software is in there, when the container image was published. These types of facts typically go in the tag. There's also a special tag named latest, which is used to refer to basically any available image that's recent. It works fine for most repositories, but we don't recommend using latest. We recommend choosing a specific image in general. That way you know what you're getting. So once you've found your image, you need to be able to pull it from a repository. And in general, the source argument for chimage pull would be URL/group/name tag. But we didn't need a URL to pull Alma Linux because Docker Hub is already the default repository for Charliecloud, and we didn't need a group either because Docker itself publishes Alma Linux, so there's no group. There are a few special images that are that way. So if we have the pull command based on the Jupyter SciPy notebook example, it would be chimage pull Jupyter SciPy notebook latest. And you will need a copy of this image for later, so you can download it now using chimage pull, or you can grab the copy that is in the training directory. If we see that I actually already have a Jupyter image file in my local working directory, so I don't need to pull this one. It does take a couple of minutes. It is a bit larger. But if you want to pull it instead of grabbing the one from the training directory, then you'll be able, doing the exercise yourself does have some value. So it's your choice. Let's talk about a different example image from the internet. Here's a software named Clara Parabricks, which is genomics software, and it is accelerated by GPUs. So here's NVIDIA showing off how much faster it is if you use one of their GPUs. And NVIDIA publishes performant builds of popular softwares on the NVIDIA cloud. So if we navigate to catalog.ngc.nvidia.com and search for Clara Parabricks, we will see that there is Clara Parabricks available. And when you are reading about the Clara Parabricks images, that page has a special button named Get Container, which will offer you an example syntax for pulling one of these images. So if you click on it, it will show you what the URL for pulling the image actually is. So in this case, the URL is nvcr.io/NVIDIA. And then the group is Clara and the image is Clara Parabricks. So it's already put together for you. So if you click the copy button on that web page, you can directly drop it into your chimage pull command. So it will be, we're not doing this one, but hypothetically, it would be chimage pull space nvcr.io NVIDIA Clara Parabricks 4321. So let's practice working with images. So there are two main image formats. There's a directory image format, which is the native format of a Linux operating system, in which there is a bunch of directories at the root of the file system, things like USR, var, etc. And in the directory format image, those directories exist on disk on the real file system. They're just not at root, they're under a subdirectory somewhere. So that's the native format for container images in general. But in addition, Charliecloud supports single file format images in the SquashFS file system format. So SquashFS isn't specific to Charliecloud, lots of applications for SquashFS, but Charliecloud uses SquashFS to store container images inside of a single file. And the reason to do that is because single file images are easier for network file systems like Lustre to handle. So you'll get better performance and be a better sharer of the network if you're using single file format images. And in order to convert between these two types, we have the chconvert tool. So if we're working with a directory image, then the image name will end in a slash, and that's your hint that it is a directory. The benefit of using a directory image is that it is writable, because it's easy to create files in it's easy to create and modify files in a directory structure, because that's just working with files the normal way. But reading and writing operations out of a directory file tree are slow. So we put directory images on the high-speed temp file system that's local to the node. Images that are in CH image storage are also directory images, but we don't refer to them using the directory image syntax. We refer to them by the name that Charliecloud uses to recognize them. So previously we had all_Linux:8. You wouldn't put a slash on that if it's in Charliecloud's image storage area. So let's have an exercise. We will convert the Jupyter notebook to a directory image. So if you previously pulled Jupyter SciPy notebook, then you would be converting it from your CH image storage, which means you provide the name that Charliecloud is using to label it. So if you pulled latest, then Charliecloud would be storing it with the tag of latest. So you would use that same tag to refer to it in the storage. And then we need to put the directory format image somewhere, and we're going to put it in temp because that is the local file system. So you need to make a directory for yourself to put it, which you're allowed to do. Go ahead and make dir temp and then your username. So $user is a convenient way to do that. I can never remember my username. It's just like got this sequence of numbers. Who could remember that? So for me, it is make dir temp user. And I've already done that. So it says I don't need to do that. I've already done that. I wonder what I have in there. It looks like I was messing with Alma Linux on a different day. So what do we need to do? You would do chconvert. After you've made dir for the temp user, you would chconvert the image you previously pulled and then a directory in temp that doesn't currently exist and will be created, and that will be the image in a directory format. I don't happen to have a directory format image in my CH image storage, but I do have this squash format image, so I'll just use that. My convert is taking longer because it's slower to unpack a single image than it is to copy an already unpacked image. So yours would have been faster if you were doing it from the CH image storage. So let's take a look inside this directory format image. If we hit that temp user Jupyter with the ls, you can see it's got a bunch of directories that look just like the root of a Linux file system. Is it the same as the root of the real physical file system? No, it's not the same. The real physical file system has some other directories like this ADM here that are not present in the image. Are there any questions so far about the directory format image? Was everyone able to make a directory format image somehow or another? We do need one to do the next exercise. So if you don't have one, you need to let me know and then take a moment to make one. Okay, so 2 people have done this. 3 people have done this. Very good. I will move on and let's complete the activity. So now that we have a directory format image, we can practice writing to it. That is the main purpose of directory format images, is that they are writable. So we need to launch a container process that sees that image as its file system, and we need to provide the write flag, which tells Charliecloud this process has permission to edit the image that it sees. So I'm just cleaning up my screen a little bit. Oops, that wasn't what I meant to do. So if I ls the Jupyter directory format image. I can see what's already there. I already have a scratch, so I don't need to make another one. So I'll just make something else. So the syntax is chrun, the path to the image, which is temp user Jupyter, and then the name of the command, which will be bash because we need a shell. And then we have to just make some things. So I already have a scratch, so I don't need to make one. So I will make something else instead. Make dir slash foo. Oh, I made an error. I forgot to provide the right flag. If I was copying and pasting out of my PDF, I wouldn't have made that error. So we can see that I'm free to create files right in the root of this file system, which would be pretty scary if you were doing that in the root of the real physical file system, but this isn't the real physical file system. This is the root of the image, which we know is just directories on disk. So it's totally possible, even if I'm not the root user. So I'm going to exit here. And if I chrun again, but without the writable flag, I can verify that the directory I've just created is still there. So these changes are persistent from one container execution to another. And furthermore, if we ls the directory structure that is on disk in temp, then that directory is in fact there. So what creating this file in the container was very similar to just creating it on disk. The advantage of creating it in the container is that if you can use installation, build and install tools that are in the container to help you. So if you're doing something more complicated than just making a directory, say you want to install some Python packages, you want to be able to do like pip install, and you would have to be running a container process for that to work properly. So that's why I teach it that way. So let's learn about that SquashFS image format. SquashFS is an open source file format for file system images. The whole file system becomes one single file. The image name ends in .sqfs. That will be the hint for Charliecloud to know what file system format that file is. And the two properties that SquashFS images have are, one, they are read-only. And the second is that the read operations are fast. So we can put SquashFS images on the network file system scratch. Any questions about SquashFS so far? Let's make sure you're still in your working area. Yes, so I'm still in my scratch space under CH tutorial. So you need to also be there. And then we will convert our directory format image that we've just edited into a SquashFS format image. And since we're not providing a path, what we mean is in the current working directory, which it will be in Scratch. So ch convert temp user Jupyter / space Jupyter.sqfs. I'm actually going to remove the one that's already there. Otherwise, it will have to override it, which would be kind of scary. So now I'm using parallel make SquashFS to pack all of those files into a single file. So now I have Jupyter SquashFS, which was created just now. And what can we do with it? We can use it for our container. We can use it as a container image. So chrun Jupyter.sqfs, which is in the current working directory, and then the name of the process. So we just launch a bash process if we just want to see some files. So chrun Jupyter bash ls, and you can see that my file named foo that I created in the directory format image is present in this Jupyter SquashFS format image. So the changes are persistent after we convert. So So that concludes working with images. Do we have any questions about working with images? So the main reason to know how to do this is if you download an image that's like 95% what you need, you just need a couple more Python libraries. You can download the image, convert it, run your pip install, convert it again, then you will have an image that can be on Scratch, has all the libraries you need, and then you can get to work with your scientific research. So that's why I teach you how to do this. So the next activities are how to work with containers. And by this, I mean how to work with the container process. So far, all we need to know how to do is create some files in the image file system. But not everything you need will be in the image file system. So we need to be able to work with the host file system. Carl is asking a question. Can I use a pulled images with other packages that were installed on the cluster? Yes, Carl, you can. It's a bit tricky, but the thing I'm going to show you next will make it clear how that happens. So if you wait a moment, I will be able to answer your question properly. So let's learn about working with containers. So we need to be able to mount part of the real physical file system in the container process so that the container process can see both files that are in the image and on the real physical file system. So in my Jupyter.sqfs container image, there's a directory named Scratch. Hopefully you also created the directory named Scratch when you were doing the exercise so that your Jupyter.sqfs image also has a directory named Scratch. But that directory will be empty. But what we can do is we can override that empty directory in the image by mounting the real physical Scratch directory on top of it. So the syntax is B for bind. There's also the long form -- bind. There's also the environment variable option, but we're just going to use the short option for this exercise. So, and then C is you're going to set what the current working directory is in the image. So we don't start in the root of the file system. You can start wherever you like. So what we're going to do is we're going to start a bash shell in that Jupyter image, but we want to be working in the Scratch directory on the real physical file system so we can see our files. So then it's chrun -b /scratch to mount the Scratch file system in the container, -c $scratch to have your current working directory be your Scratch directory. If you're still running a container image, you would know because your prompt would be different. So don't forget to exit your container image if you're in a container. And so you're not in a container because chrun doesn't work from within a container. That would be like inception. So back on the real physical file system, it's chrun -b. Oh my goodness, something bad happened. I lost my connection to the remote server. Did I lose my connection to Zoom? I think I'm still connected to Zoom, but Portal Aces is mad at me. Okay, I am back on login 2. If you got kicked off of login 2, perhaps it rebooted, in which case we'll need to repeat a little bit of our setup. So what parts of our setup? We'll need to cd to our Scratch area in the ch tutorial, and we need to module load Charliecloud. At a minimum, we'll have to do those two things. And now I think I'm ready to do the exercise. I guess I should give people a moment to confirm that they're caught up again if you also got kicked off of your login node. And I will report that to the system administrators so that they know something happened. And now you have landed on a different login node. If you're on a different login node, you won't have your ch image storage, but you should still have the squashfs file in your Scratch because Scratch is a shared file system, so it will appear on all the login nodes. thankfully, if you did complete that exercise to create a squashfs file in your Scratch, then you're ready to proceed. We don't need the directory format image again in the course. So that will be fine. Would anyone else be willing to throw a thumbs in chat if you confirm still have your squashfs file in your Scratch area? You ready to proceed? Okay. I'm glad it happened after we made our squashfs files. What is path? Sorry, I'm not understanding the question. Where are you seeing the word path? Oh, so I am in my Scratch directory in a directory I created called ch_tutorial. Do you remember what your current working directory was when you created the squashfs file? If you forgot to change directory to Scratch, then it might be in your home directory or somewhere else. Okay. So we were about to do this, right? I think this is what we were about to do. So it's chrun binding Scratch, current working directory in Scratch, Jupyter.sqfs bash. I'm actually going to copy that out of my PDF because it's a bit long and I don't want to make another typo. So this is slide 36. So I'm scrolling to slide 36 in my PDF. And now I can copy directly out of my PDF. It decreases the chance of a typo. So my prompt has changed, which means this is a container image, but you can see that my prompt contains the path to my Scratch directory. And if I do ls, there's lots and lots of files in here. These are my personal Scratch files. So if I cd into chtutorial, I can see my chtutorial files, including the image that I'm currently running the container out of. So that's a bit funny. But the point is that if there's any files in Scratch I need to be working with, now I can easily do that. Tanaza has an error. Can you describe your error? Can't make dir. It sounds like you might be in a container already. Can you check if you're already in a container? And if you are, type exit. If you're in a container and you type exit, then your prompt will change to aces-login, username at aces-login. Okay, then you need to just try again. Do you happen to know which login node you were on? Because sometimes one of the login nodes will get, yeah, login 1 sometimes gives me trouble. Try again, but hopefully you'll land on a different login node that won't give you trouble. Login node 1 sometimes gives me trouble, and I don't know why. I'll report it to the system admins. Okay, I believe I actually completed this. I believe I actually completed this exercise while I was talking. Carl noticed that aliases weren't available in the bash container. So Charliecloud is very lightweight, so it has very few defaults. And the default behavior for any container is always going to be getting a fresh login with no variables. If you want to pass in variables from the outside, that's always going to be either a feature of your runtime or an option that you specified. And since Charliecloud is very light on defaults, you will always have to specify if you want to pass in your external variables. It is possible. I think we may have a chance to see that later. But you'll be manually doing that for each thing that you need. Other container runtimes like Singularity are designed differently, and they are more of a it works by default type of solution. So if you're in Singularity, you probably will have your shell variables in your container. That's just a slight difference in philosophy as to what is the default. But it's not a problem. It's just extra work to do if you want your bash aliases to work inside the container. Oh, next slide, working with variables. So we've seen how to work with files, and now we'll learn how to work with variables. So if you, so there's two kinds of variables in a container. Generally, there's variables that are defined by the container image, and then there's variables that are defined outside the container, and you want to pass those in. So for both of them, we have the setEnv option. If you use the setEnv option with no argument, then it means set the variables that are defined in the container image. And if you provide an argument, it means set this variable that was defined outside the container image. So your bash alias would be an example of some variables that are defined outside, although I can't quite remember how you do that. You might have to do something like pass in a function and then execute it. Like I'm not the best at aliases, but it would be possible, that being the material point. For this exercise, we're going to set the environment variables that are defined in the image. So an example is Python has a variable named Python path, which tells it where its libraries can be found. When we downloaded Jupyter, we got it from a repository named SciPy Notebook. So we know some scientific Python libraries are installed in the image, but Python will only know where to find them if Python path variable is set. So that variable is defined in the image. So to make sure it's set, we just have the setEnv flag. So that's chrun. Gosh, I am struggling. Let's just copy it out of the PDF. Yeah, we'll do that. So chrun setEnv Jupyter squashfs Python, and now we can do import numpy. Anybody here comfortable with what did I do wrong? Oh, right. You don't need parentheses on an import statement. Import numpy. Oh my goodness. Import numpy, print numpy. Anybody here a Python user comfortable with numpy? So it says numpy was found at the location opt-conda lib Python 3.11 site packages. So that's a common location where conda would install site packages. So apparently the Jupyter group used conda to install the scientific Python libraries into this image. Get some free facts for you. So I'm going to use the Python exit function. And that ends this running process. And since we didn't have a bash process in the image, so we didn't have a bash process running in the container, we had a Python process running in the container. When you exit Python, the whole container is done and you're back on the real physical file system. So for contrast, I'd like to show you what happens if I don't use setEnv. It says it can't even find Python because the path variable is not set. But I could do something like usr bin Python to say, I think it's there. Well, it's got to be somewhere. Maybe it's under opt-conda. Oh my goodness, I'm embarrassing myself. Yes, it was under opt-conda. But then if we do the import numpy, oh, well, apparently I'm wrong. If you provide the path yourself manually on the command line, then it knows where to find things. But if you didn't want to provide the path to Python, then you have to use setEnv to make sure that path is correctly set. Were there any questions about the setEnv? Did you want to try? I'm going to try setting an environment variable from the outside because I wanted to answer the question. So if we read more about how setEnv works, it's setEnv equals arg. So let's see if we have any decent environment variables. We have a bash function module, right? I wonder how you do that. Does that count as a variable? I actually don't know. No, that doesn't seem to work. But we can pick one of these other ones like module path root. So I could go chrun set env equals module path root space Jupyter bash. Did I make a mistake? Which mistake did I make? Guess I need to check the manual. Oh, okay. If you just do file, if you only have one, then it says go look for a file with your environment variables. So I guess what I needed to do is I needed to go module path root equals module path root. There we go. And now if we look at environment variables inside the container image, we can see that module path root should be in here. Yeah, it is. I don't remember how to get aliases into the container, but it has to be possible. I just I would have to go and learn more about that. I don't know off the top of my head. So only one more topic left, I think, in this section before our break. The last thing we're going to do with the Jupyter Notebook SquashFS file is we're going to launch the Jupyter Notebook, because what's the point of having an image with a Jupyter Notebook if you can't even use it, right? So we're going to try interactive graphical computing if you have a copy of the Jupyter Notebook, or if you're using a copy out of the training directory. Either way is fine. You can still do this along with us. So you go to the portal and you click on interactive apps in the portal menu, and you find the Jupyter Notebook. And the Jupyter Notebook has a form, and the form starts with a type of environment, and it may be on Anaconda by default, so you need to pick and scroll down to containers. And it was on containers for me because I've previously done this. And then you need to type in the path to a container image file. So you can see in our slideshow that we have a path to an image file. So you may have named it Scratch CH Tutorial Jupyter SQFS, as I did, but if you didn't, you can take the backup copy out of the Scratch. So you could go copy this off of the PDF, paste that in here, that would work. Or you could copy this out of the PDF and paste that in here, if that's where your file actually is. And the variable is okay because the variable gets evaluated on a node where the variable is defined. So that will correctly expand to a real directory. And you do have to provide the extension .sqfs because that's the hint to the app as to whether it's going to try to load it with Singularity or Charliecloud, which are the two supported options for this. You pick a node type. If it's not CPU only, probably just CPU only is fine. I think we do have a reservation, but this won't use, I don't think this will use the reservation. So this might just be sitting in the queue for a while. If it sits in the queue for a long time, then we won't have a chance to do the activity, but it looks like it will be able to start. So that's good news. So I'm going back to my slideshow, and after you click start, then you have to wait for the job to start, after you click launch, you wait for the job to start. Then you can connect to Jupyter, and if you're familiar with Jupyter, this will make sense. Connect to Jupyter, create a new notebook. And you can see that Jupyter has dropped me into my Scratch area, and that's because the Scratch area is getting bind. And we can just start a new notebook and do the same thing, import NumPy, print NumPy to see where NumPy is coming from, to verify that we are in fact running in that same container. So this is the same container, so NumPy is found at opt_conda. How do we know that's correct? Because if I try to hit opt_conda with an ls on the real physical file system, there's no such directory. That's a path that exists in the image, not on the login node or on the compute node. So I'm actually done with this exercise, so I'm going to shut down my Jupyter notebook. And then on the interactive set, if you shut down using that one, then the interactive session card changes to completed. Would anyone like to throw a thumbs up in the Zoom if you have successfully completed this activity? I'm not seeing a thumb, so I guess people are still waiting for their jobs to queue. We can take a moment to wait. I shut down my job, so hopefully yours will queue soon. If you picked the CPU partition with just the one core, it should be able to start. PEStat pCPU. Looks like most of the CPU nodes are in use right now. But there are a few that are only partially used. Like this node is 84 out of 96 used. So you can squeeze in if you only need one core. Theoretically, anyway. Who knows if it'll actually work. If this one doesn't work for you, it's not a big deal because the other activities we're doing today, we have a reservation for those nodes. It was just this one that I don't have a reservation. And that would conclude this section, because the next section is we're going to talk more about those scientific applications. So that means we're on break now. So let's take a longer break, 10 minutes. So we were on break until 32 minutes past the hour. So in my time, that's 11:32 because I'm on Central Time. But if you're waiting for your interactive session to launch, then you might be able to get that to happen while we're on break. When we come back from the break, we'll have to move on to the next activity. Howdy, students. Welcome back from your break. If you weren't able to queue for that node to test Jupyter, then I apologize, but we do need to move on to our other activities, which will work correctly because we have a reservation for the other activities. So we will be learning about some containerized scientific applications. I have a handful of examples prepared. I don't know how many we will get through. Might get through all of them or some other number of them. I don't think it matters a lot because they're pretty similar. So we'll start with machine learning with TensorFlow. TensorFlow is not my favorite machine learning package, but it is an example of pulling an image that is for a specific hardware. And this one is for the CPUs that we have on ACES. We have Intel CPUs on ACES. Sapphire Rapids, for example. So this TensorFlow was optimized to use the instruction set for those Intel CPUs. Now, modern machine learning, you're probably not doing on CPUs anyway. but this is just an example of something. So the Docker Hub is the source for this repository. So it's in the Intel group owned by the Intel Corporation, and they have public, and their repository is Intel optimized TensorFlow AVX 512. So that's images that are optimized for this type of Intel CPU instruction set. And so if you do ch image pull, you don't have to include the URL for Docker because that's the default anyway. So it's just Intel, the name of the repository. And then, of course, the next thing you would do is you would convert that to Intel TensorFlow.sqfs. If you're interested in TensorFlow, I have an example here of using TensorFlow within Python to check that it works properly. But we won't be executing like training or anything like that because we don't have time for that today. Normally machine learning training takes a while. We have other examples. I think we have a PyTorch example somewhere, but I didn't prepare one for you today. Anybody here doing machine learning with Python? Is that a popular use case? If you're doing machine learning, do you want to tell me if you're using PyTorch or something else? Okay, so we have one responder who says PyTorch and another who says using TensorFlow. So Tanaza would like to try, would you like to try the TensorFlow with the container? Might be more educational. We can try this one. So we have a backup copy of this image. So you don't have to do the pull operation, which will be slow. So you can just provide this path to this image after the ch run. So if I go to my slideshow, I'm on slide 43, you can just grab the path to this image and in your login node, ch run, drop in the path to the image, bash. So start Python, import. How does it work again? Import TensorFlow as TF. And it's printing out a fun fact. This TensorFlow binary is optimized to use available CPU instructions in and then AVX 512, and then some CPU instructions I really don't know anything about. Print TensorFlow version. I'm going to print TF, and we can see that it's installed at USR lib local lib. Invalid character. Okay, so if you're copying and pasting out of my PDF, it might not copy the quotations correctly because Python only respects a certain type of quotation, and this is not it. So you can see if I delete it and retype it, it looks different. So like the spicy quotations don't work. Unfortunately, I don't know how to make that not happen. You just have to delete the quotes and replace them with normal quotes. TensorFlow 213, apparently. I don't know why we have a different Unicode character for spicy quotation mark. I would not have made that choice. Or if I was the Python developer, I would have just had a very long list of characters that I recognize as a quotation and say they're all the same to me. They're all just quotation. Okay, so I'm using the Python exit function to stop this process. I'm using the bash exit function to stop this process. And now I'm back on the real physical file system. Tanaza, are you satisfied with this TensorFlow exercise? I see thumbs from Tanaza, so we're ready to move on. How about LAMMPS, molecular dynamics? Anybody here interested in chemistry or material sciences, LAMMPS is sometimes used in those fields. My favorite fun fact about LAMMPS is the animated logo. So if you click on the link and mouse hover the logo, the atoms dissolve. It's just too fun. I can't help myself. I have to come here and do that every time. Okay, so where do we get our GPU ready container images? Well, who's better at building GPU ready software than the GPU manufacturer? So we have NVIDIA GPUs on ACES. So let's take a look at the NVIDIA cloud. So if you search LAMMPS in the NVIDIA container registry, you'll see that they have container images with LAMMPS. And one of them in particular works with the H100 GPUs, which are the current generation of GPUs, the Hopper GPUs, and the ones that we have on ACES. So you would, in theory, click that copy button and you would do chimage pull nvcdar.io / the rest of that. But you don't have to, because we do have a copy on disk. So if you want to try it, but you don't want to pull it, we do have a backup copy. But if you are going to be doing this exercise, it probably is worth pulling it. So, but we're not ready to pull it yet because we have to be on a compute node where the H100 GPUs are. And we'll talk about that in a moment. Anybody here interested in using the H100 GPUs today? Would you please give a reaction in Zoom if the GPUs are of interest to you? Even if you're going to be doing machine learning, the process will be similar, so you will learn something. Okay, thank you, Carl and Yuiche and Tanaza, for your thumbs up. Let's talk about what we need to use GPUs with Charliecloud. So in order to use GPUs with Charliecloud, we need two things. We need the NVIDIA libraries. And the NVIDIA libraries are separated into two parts. You have the CUDA toolkit, which is publicly available. You can download that, and it's already in the container image. But then you have the other part of the NVIDIA libraries, which is the drivers. And the drivers are never included in the container image. And I think that's mainly because they're really protected. They don't want to distribute the drivers to just anyone. You really have to subscribe to get the drivers. And the other reason is because the drivers are specific to that GPU. The CUDA toolkit works with almost any NVIDIA GPU, but the drivers are specific. So we get drivers from the compute node where the GPU is. They can't be found on any other nodes. They are not found on the internet. So when you're setting up to use GPUs, you have to be on the node where the GPU is to find the drivers. Thankfully, you don't have to find them by hand. We have a tool for that. It's called the NVIDIA Container CLI tool. Its job is to find where the drivers are on disk. And then the ch from host tool takes the output of the NVIDIA Container CLI tool and says, each of these files, I'm going to copy them into the container image. So then the container image becomes a container image that's specific for this GPU. The one you get from the NVIDIA cloud is generic for any NVIDIA GPU, and then you turn it into a specific for this GPU. And the other thing you need is an NVIDIA run script. Now the run script is already in the container image, but Charliecloud doesn't by default know how to use it. We need to turn it into a regular file. So I extracted the run script from the image in advance. So all we have to do is copy it from the training directory as a regular file. So on ACES, we have to get to a compute node. We have to load the NVIDIA Container CLI. We have to do a from host operation, and we have to get a copy of the run script. So those are the pieces we need. So the first thing we need to do is get to a compute node. If you are on a compute node already, in a previous version of this course, you were on a compute node already, so you had to get back to a login node. But you're already on a login node, so you don't need to type exit. What we need to do is get to a compute node using srun. So srun is the slurm command for I want to execute a command on a compute node. We're going to get a bash terminal. So it's srun bash. We're doing bash on a compute node. And the rest of these are slurm flags that say, here's how much resources I need on the compute node. Because slurm is a scheduler. You have to ask for resources. So you have to say, I want to be on a node that has a GPU. I want one GPU that is an H100. And I want to be on the node that's reserved for this course. And I'm going to be using 16 cores. It doesn't really matter how many cores you pick, and just pick the number. So this is slide 47. So please scroll to slide 47. But remember, when you, right, so what happened is probably when you pasted all in one line, it didn't get a space between these two characters. So you just have to be more careful. So I copied in 2 steps. I've copied this part onto my terminal. And then I hit space because I have very bad luck copying this all in one line. Doesn't work for me. And then I paste the rest of it. And you can see my prompt has changed. Instead of ACES login 2, I'm now an AC96. And then we would like to know if this node has any GPUs. NVIDIA SMI. And yes, we have an H100. Were you all able to get to a GPU node that has an H100? Go ahead and give me the thumbs up in Zoom if you are on AC96 or a different one that has an H100. Yuchie has reached AC96. Carl has reached a node. Very good. Anybody else wanting to do the GPU exercise with us today? Also 96. So AC96, I think, has more than one GPU, so we can share it. Jofe would like to be on a node. Jofe, are you on a compute node with us? I can see that 4 of us are on this compute node, which means there probably is another compute node. Oh, Jofe, you're working with Charliecloud on a different cluster. Okay. Jofe, do you have H100s on yours? Okay. You might need a copy of the run script. I can give it to you directly. It's just a small file. Okay, if you can get to an H100 node and you have Charliecloud, you should be able to do this, but I might need to give you a copy of the run script because that's a little bit tricky if you haven't done it before. So now that we're on a node, it may have reset our modules, but we need a couple more modules. So we're going to be setting our variables again in case they got lost. So if you don't have a training, you have to reset it. If you're not in your Scratch, you have to CD to it. And then if you don't have Charliecloud, you'll have to load it again. And then we'll have to load these other 2 things. So I'm currently already in my looks like I don't have my training variable, so I'll have to create it again. I'm currently already in my Scratch directory, so I don't have to change directory, but I did have to create that variable. And then we have to do module load Charliecloud. NVIDIA Container CLI and web proxy. So on ACES, NVIDIA Container CLI is available as a module. If you're on GACRC, I don't know where you're going to get that one from, but it's not complicated. You literally just need like one file. I could probably tell you where to get the one file from. Web proxy. So on ACES, the compute nodes aren't connected to the internet directly, but you can get to the internet via a proxy. So loading the web proxy module just sets that up. And now we have a multiple steps to get the image and insert the needed pieces and run it and convert it into a squash FS. Joufei, do you need a copy of the run script, or are you not doing this with us right now? Okay, I'll just get a copy of the run script. We have in our training directory, we have a run script. I'm making a copy of it and with CP. I'm going to download it. And let's see if I can put it in the Zoom chat or something. Is there a way to share files in Zoom? I don't know. I guess I could email it. We have Joufei's email, right? Joufei, yeah, that's helpful. Thank you. So the run script I didn't create. It's actually already in the container image. Just Charliecloud doesn't know how to bind it. So we have to turn it into a regular file. Okay, I'm sending that. Run the commands on slide 49. Yes, we're on 49. That's what I'm about to do. I just want to make sure that Joufei is able to follow along. So in my path variable, I have the NVIDIA Container CLI, which just contains the executable named NVIDIA Container CLI and NVIDIA Container libNVIDIA Container so.1, which is like just a very small number of files. So if you have NVIDIA Container CLI installed somewhere, you would know because the command NVIDIA Container CLI would say that you can use it like this. It's not particularly difficult to install. I just don't know if you have it already or not. All right. So for everyone else, it's time to execute the commands on slide 49. So we're doing ch image pull and copying this specific version of LAMMPS. And it does take a moment because it's not small. Then we're going to convert the image into a directory format, which means we need to put it in the local file system. So tempdir, TMPDIR, is a path that Slurm gives us that is on the local file system. So that's a place that's safe to put a directory format image. Now that we have a directory format image, we can modify it by injecting the NVIDIA drivers, ch from host NVIDIA, We can modify it by injecting the run script. I actually have a copy in my local directory, so I guess I'll use that one. And then we finally convert that into a SquashFS, which again will be slow because it is not small. It wants to use 96 processors because I didn't tell it how many to use and it just guessed. But I remember I only requested 16 cores. So when 96 processes are fighting over 16 cores, that's not very fast. I guess you could consider that to be like a bug in Charliecloud, that it doesn't have a way to correctly know how many processors to use. I actually reported that bug to Charliecloud. I don't recall if it's been fixed, but it has not been fixed in the version that we have installed right now. Carl, thank you for joining us. I hope you will give Charliecloud another chance on another day. But if you were able to do any of these activities, then you have already learned a lot about Charliecloud. So I don't think you're going to be sad about missing out on the remaining activities. They're pretty similar to what we've already done. So Singularity, modern Singularity installations are pretty much fully unprivileged. They're technically not. The system administrator installs them, but they have all the same unprivileged features that they have, not the identical. They provide similar unprivileged features that Charliecloud does. So for example, an image builder, Singularity has an unprivileged image builder feature. So there's no reason not to use Singularity. From the perspective of the user, it has the same features. From the perspective of the system administrator, Singularity is pretty well accepted by the community as safe enough. But if you don't like that, I believe Apptainer, which is a fork of Singularity, has a fully unprivileged option. So probably even if you're worried about Singularity, you still have an option that's effectively the same thing. So I'm not going to tell anyone that Charliecloud is better than Singularity. As far as I know, that's just a preference. Which one fits your style better? But that being said, being unprivileged is very preferred over being privileged. So the modern container runtimes, Charliecloud, Singularity, Podman, they all have unprivileged options that work well. So any of those would be acceptable. But the older container runtimes, Docker, older versions of Singularity, older versions of Shifter, these are the ones that are privileged container runtimes, and they I would never recommend because they introduce a huge security risk or they skimp on features we need, like not having the ability to build images or not having the ability to manage network operations. And so unprivileged really is the way to go. But that being said, in modern terms, recent versions of Singularity are basically already unprivileged. So I'm not worried about that. Have I managed to answer your question in too many words? Okay, Carl, I hope you have an excellent day and I hope I have not made you late to your next appointment. Um, Gosh, this make squash FS operation sure is slow. Is anybody doing make squash FS with me on this node? Like we're probably all waiting for the same thing. Yep, it's exactly what I said. You can install Apptainer unprivileged. There is an option for that. So Apptainer is basically the same as Singularity. So if you are a Singularity user, you do have an option. So there's no reason not to want to use Singularity. Yuchia says he has finished. Tanaza says finished. Excellent. So that means we're ready to test our new container image. So we have a LAMMPS Squash FS that's brand new and it weighs as much as a brick. Gosh, look at that. NVIDIA does not make small containers, so that is not their purpose. All right, so now we need to be able to test the container. So we need the run script to be in the container, which is why we needed it to be a regular file so we know where to find it. We need to set env because LAMMPS has environment variables. And of course, the syntax for LAMMPS is MPI run LMP. Anybody used LAMMPS before? Familiar with LAMMPS? Well, it says it can do some stuff. So let's try benchmarking it. So I have a benchmark prepared, which is the Lennard-Jones benchmark, probably the smallest benchmark ever devised for LAMMPS. So you just need a copy of the input file and the benchmark script from the training directory. So let's do that. Actually, I already have those files, but it would be CP $training benchmark to here, and then CP $training in .lj to here. Then you have the files. And you need you don't need the run script anymore because it's actually inside the container image because we copied it there using the from host operation. So then it's all in one line. ch run set env -b. So this time we're binding the real physical file system, but instead of binding the entire Scratch directory, now we're just binding this current working directory. And the container image has an empty directory named host pwd for that purpose. So we're just using it, but it's not a big deal. If you wanted to bind Scratch, you could do it the way we did it before, where you just make sure there's a Scratch and then you bind it. And then I have to hit space because I'm copying one part at a time. So it's chrun set env bind the current working directory, start in the current working directory using the LAMMPS image. And then the command is run script in the image bash benchmark.sh. I neglected to make benchmark.sh into an executable. Otherwise, it would be run script /benchmark.sh. But I didn't bother, so it's bash benchmark.sh. And the key line here is that it will use up to 1 GPUs per node. Do you see that line? If you see it will use up to 1 GPUs per node, then you know you're benchmarking the H100 GPU. Total wall time only a few seconds because it wasn't that many atoms. It was only 2 million atoms, 100 time steps. That's not so much. It's enough that you know you turned on the GPU and made it do something, but at 100 time steps, you're not optimized. You're still basically loading things into memory at that point. So the performance is not guaranteed to be accurate. But still 50 million atom time steps per second is not too shabby. Tanaza, you said you're familiar with LAMMPS. Were you able to try this benchmark? Did it work for you? Very good. And do you feel anybody here who wants to learn about Clara Parabricks today? Because I do have a genomics activity prepared, but it's not known to me whether that is of interest to anyone. I'm not the biologist in our group, so I wouldn't even really be able to answer your questions about it. Tanaza, not so much interested in Clara Parabricks. Juofei, you interested in Clara Parabricks today? Chia, are you interested in Clara Parabricks today? Sajesh, Juofei says you are interested. So in order to do Clara Parabricks, we're going through some similar steps, but at the end you have to have a bunch of input files. We have these input files in our training directory on Faster. Do you happen to have any Clara Parabricks input files available on your cluster, Juofei? I recall you said you were working on the UGA cluster, Georgia CRC, something like that. If you don't have any Clara Parabricks input files, I don't see how you'll be able to do the exercise. Tanaza, thank you for reminding us we have a survey. So my last slide is a survey. We have a QR code if you'd like to take a picture of a QR code, or I will just drop the survey in the Zoom link chat. So for those of us who are not interested in the Clara Parabricks activity, which is very similar to the LAMMPS activity, but it just requires different input files. If you're not interested in that, then you are done learning about scientific containers today, and I would love for you to take our survey to let us know how we did so we can improve for next time. Otherwise, I suppose I will be walking Juofei through a Clara Parabricks exercise. Juofei, I'm sorry, I maybe got confused. Oh, okay, you don't need help with Clara Parabricks today. Then I guess we'll be skipping Clara Parabricks today, and that concludes our short course, so we're finishing a little early. I hope you have an excellent week and enjoy the use of containers, whatever form that takes for you. I'm glad you found the workshop to be very helpful. I have also previously recorded this workshop, and those recordings are on Zoom. So recordings are on YouTube. So if you wish to review the materials or look at one of the other similar courses, you can go do that and look at our YouTube channel.